Welcome to the second part of Lecture 12, The Sensing Revolution. This lecture is part of the subject Future Farming Technologies, which is a component of the Bachelor of Agriculture and Technology, a degree offered at both North Melbourne Institute of TAFE and Melbourne Polytechnic. Please visit our website at www.nmit.edu.au for further information on this course or other courses that we offer. My name is Dr. Nikki Cooley. Please ensure that you have watched Part 1. This is an introduction to sensing and lays the groundwork that you will need to understand in order to complete Part 2. In Part 2 we will look at specific examples of sensing technologies in agriculture and some of their applications. There are 3 student learning objectives for this lecture. You will describe and explain the interrelationships between this particular technology and production efficiency in agricultural industries. We will look at sensing, as in student learning objective number 2, and we will touch on some of the appropriate terminology and communication processes for this technology. Sensing climate is one of the most important sensing requirements for agriculture. Climate impacts on nearly every component of agricultural production. In this part we will look at the sensing of temperature, wind direction and speed, rainfall, humidity and light interception. Sensors that sense a climate are typically called and constructed as part of a weather system or weather station. It is important to realise that they are a collection of sensors and that each of these sensors works on a different technology and assumptions. One of the most useful resources for sensing the climate has to be in Australia the Bureau of Meteorology, which is just an exceptional resource that you have available to you. Growers and farmers use this information either directly by logging onto the site and getting regular updates, or indirectly as it underlines the data that is collected here, underlines all commercial weather station outputs. The Bureau of Meteorology measures and predicts services. It also conducts research to enable more robust predictions. Elders provides an example of a commercial weather service. You can click on any one of the regions you are farming in and get regular updates. I believe they connect this to certain algorithms which they can offer services where they enable weather predictions so that you can work out when to apply your fertilizers, and some disease prevalence for some industries such as agronomy and viticulture and perennial horticulture. Measuring climate can be highly variable and very subjective to the area that you're in. A commercial weather station, such as that provided by BOM or information provided commercially from a company such as Elders, can give you some good information. However, there may be applications and production efficiencies that you are trying to use where you need more further or localized detailed information. In this situation, you would construct your own weather station on your farm or in your vineyard. Weather stations are also used extensively in research. The link on the screen shows one commercial example of a high-end weather station. This is the Vassala Hydromet system. It is used a lot in research activities. You can view the technical specifications. This shows you what the weather station constructs of, what parameters it measures, how it measures them, and what range of measurements you can expect to find. You need to match all these technical specifications with both your area, and you need to ensure that the weather station that you are going to use is suitable for your geographical climate or communication abilities and areas. There are many examples of weather stations, and as part of one of the tutorial tasks associated with this topic, I'd like you to research 2 commercial weather stations and put your information in here. As part of your research, you will list what is measured and how the technology works. You will try and get an understanding of the price range and the instrument specifications. You will think about the power source. Is it batteries, mains or solar powered? And you will find out any routine maintenance that is required for your weather station. Ideally, you will find an example of a very cheap weather station and a more expensive one. You can compare the technological differences and the robust differences. There may be also differences in measurement frequency and the range of measurements. There is an area of climate measurement that goes under the umbrella of atmospheric remote sensing. Remote sensing is an area of science in which different methods are used to measure and study objectives remotely. This enables you to obtain information about an object without being in physical contact with that object. At the SMHI research in the area of satellites and radars, preliminary concentrating information on precipitation and cloudiness is carried out. This research is directed towards operational meteorology, hydrology and oceanography, but it also looks at climate research too. A great part of the research is done in international projects where cooperation takes place with several other European communities and with so-called satellite application facilities. While much of this technology is not used directly in agriculture at the moment, certainly the outputs of this kind of research are used indirectly, in both understanding weather systems and enabling better and more robust modelling of what the future climate may hold for us. This image shows thunderstorms over the southern Sweden area and is an example of the kind of remote weather sensing data that one can obtain. Soil sensing can be conducted in a number of ways, and what I mean by that is there are a number of different methodologies which underpin this area of sensing. Some of the examples that we are going to look at are the more commonly used ways of soil sensing. There is neutron probe technology, time domain reflectometry, or TDR for short, methods of gypsum blocks, and methods of capacitance probes. Soil moisture sensing certainly has led the way in sensing in agriculture. It all started a few years ago by the invention of the neutron probe sensor by Dr. Peter Cole. He was working for CSIRO at the time. He, since this date, commercialised his sensor and now operates a successful business that not only still sells the neutron probe technology but also other technologies for both soil and plant sensing. The device works on a simple concept. It emits neutron particles of radiation. One of the features of neutron particles of radiation is that they move very fast and they can be easily measured. The fast energy that is emitted from the probe ensures that a certain amount of energy collides with a soil particle. This results in the slowing down of the neutrons. There is a relationship between the amount of moisture in the soil and how quickly the neutrons slow down by. The speed of the returning neutrons is measured by the probe. Calibrations are required to set up the measurement correctly. They are required for different soil types as there is different relationships of neutron speed, structure and soil. In order to differentiate the structure component of the soil and the moisture, these calibrations must be conducted. The operation of the neutron probe is based on first installing aluminium access tubes. They are installed in various locations around the enterprise, wherever the farmer would like to measure or determine soil moisture. One aluminium access tube will give you one reading of soil moisture. The probe is placed into the aluminium access tube. Neutrons are emitted from the probe where they collide with hydrogen atoms in the soil. Because this is radiation, an operator needs to have a license in order to operate the probe. There are considerable health and safety risks if the probe is not used correctly. Once the neutrons hit the soil, returning neutron speed is measured by the probe, and a conversion of neutron speed can be made to give you a result of millimeters of soil moisture. So let us review some of the advantages of neutron probe sensing technology. The area of measurement is very accurate and large. A neutron probe can cover a 1 meter radius of the soil probe. A total root zone measurement can be obtained for most crops. Reproducibility of the measurement is excellent, and the unit of measurement is in millimeters. All of these components make the measurement of soil moisture by a neutron probe very applicable to the agricultural industries. The data can allow irrigation scheduling such as RDI and PRD to be implemented as long as regular measurements are collected. And due to such a large area of measurements, less tubes are typically required to get the spatial dynamics of your vineyard or paddock. All sensors have a mixture of advantages and disadvantages. The neutron probe sensor disadvantages are that they require training in operation of this equipment. There are health and safety and functional aspects where the training is required. Some operators have removed neutron probe detection from their operations due to the OH&S concerns, such as the company Treasury Winder states. The operators not only require a large degree of training, they also require accreditation to use the probe. If they use the probe without the appropriate accreditation, they are breaking the law. If you are using a consultant, you may have to use them or employ their services regularly, particularly if you are relying on this information to set your irrigation practices throughout the season. And probe's accuracy is questionable in the top 100 millimeters of soil surface. This is particularly important in crops where there are many shallow roots, such as some pastures. It is also important on crop establishment, as often it is this area of the soil that you are most interested in. Other disadvantages to this technology is that the data has to be collected manually. That is, it can't be automated, unlike some other soil moistures. A lot of resources are required to get the temporal information. What I mean by this is if you wish to know how the soil moisture is changing over a 24-hour period or over a week, you need to take many measurements. The spatial resolution, or how much water there is in your whole farm, of the probe measurement is based on the number of access tubes. If you have a lot of access tubes, the spatial resolution can be good. However, to obtain good spatial resolution, you need to do a lot of resources, as the data collection is manual. Now let's have a look at a very different type of soil sensor, that of time domain refractometry. The name gives an indication of how this sensor operates. The measurement is based on the soil water content and bulk electrical conductivity measurement of the soil. It evolved around the 1980s with a suite of publications by Top and Dalton. The operation of this technology is based on placing a TDR probe into the soil. The probe sends out pulses that are then detected on their return. The displacement of the signal is related to the moisture content of the soil. Commercial systems become available in the late 1980s and continue to evolve with TDR instruments, probes and multi-mixers. The unit of measurement appears as a percent of soil water content. Measurement can be automated, thus giving it excellent temporal resolution. A list of some commercial examples of TDR can be found at the following website. The TDR method relies on a very fast time or change step voltage increases. The voltage is injected into a waveguide, which is usually constructed of a coaxial cable. This coaxial cable carries the pulse to the probe, which is placed inside the soil or the other porous medium. Figure 1 demonstrates how the relative voltage or impedance is connected with the distance from which the signal is sent. There are several advantages when using TDR to collect soil moisture data. It has excellent temporal resolution, particularly when your system of sensors is connected to a central system, either via wireless communication, such as a radio, or through a wired system. This particular attribute allows a very important application, that is that this data can be used for both a manual and an automated irrigation scheduling. That scheduling system, of course, is based on soil moisture depletion, or how much water is in the soil, then how much is theoretically removed or used by the plant. This technology does not need any specialized training to operate it. There is no specialized qualification or certification to install, but installation procedures must be followed closely. The cost for each individual probe is relatively low. If a large area, that is, a large spatial component, is required, then costs can rise. Costs are also dependent on the mode of communication you may employ. The probes can be used in most soil types under a range of soil water quantifications. There are some disadvantages of using TDR to measure soil moisture. Like many of these small probes, the spatial resolution is dependent on the number of probes you install into your paddock or across your farm. Therefore, spatial resolution for this kind of technology tends to be low. The area of measurement of these probes tends to be only 1 to 2 millimeters immediately around the probe. Therefore, you are measuring a very small area of soil. If you have soils that experience large fluctuations in soil moisture, i.e. 1 minute they're very dry and the next minute they're very wet, this can lead to problems in the accuracy of your data, as the movement of the soil can remove contact around the probe. The data accuracy of the probe depends on correct probe installation. Another type of soil sensing is called gypsum blocks. This technology is constructed from blocks made from gypsum, and hence its name. The operation is quite simple, and you can almost think of it as a sponge. The gypsum block will absorb water. The gypsum block is installed in the soil, and any water that is in the soil will reach equilibrium between the soil and the block. Once equilibrium is reached, the concentration of water in the block is measured by simple voltage differences through the block. One reason that gypsum blocks have such a great uptake in the industry is that these units tend to be very cheap. They're quite simple. Gypsum, voltage, and a measurement of voltage. Because of their cheapness per unit, there is a great potential for increased spatial resolution across your paddock and your farm. The unit of measurement is very different to that of other sensors. It's not as a content or an amount, but rather an available soil moisture. What we mean to this is that the number relates to how much water is available for plant uptake. This is very important in scheduling. Recently, because this technology can now be automated, you can integrate gypsum blocks data into automated irrigation scheduling systems. There are some disadvantages for using gypsum blocks to measure your soil moisture. There is only a small area around the probe which is measured. In the manual version of the sensor, of which there are many around, the temporal, or data over time, collection is poor. Data can be an issue with large soil fluctuations for this sensor. If a soil stress is required, such as in viticulture where regulated deficit irrigation may be required, a measurement outside the range of the moisture may be required, which stops this sensor being able to be applied for such an application. This sensor can be at a disadvantage on sandy soils, and calibrations are required. Capacitance and TDR techniques are two methods that are also used as part of soil sensing technologies. They are often grouped together because the technology that underpins them is similar, but it is worth noting they are not identical. They measure the dielectric permittivity of the surrounding mediums. The capacitant technique determines the dielectric permittivity of a medium by measuring the charge time of a capacitor, which uses that medium as a dielectric. In the associated tutorial with this lecture, you will be required to do a tutorial on and an exercise on capacitance sensing technologies. Please complete this tutorial and insert and put into your lecture notes at this point. EM38 are another kind of sensor that enable you to measure both soil texture and soil moisture at the same time. They output a map of your soil, giving either variations in texture and or moisture. The advantages of using EM38 technology to get a sense of your soil is they give you excellent spatial soil structure information and resolution. They can measure any soil depth profiles, for example 1 to 1 meter or 1 meter to 30 meters. It depends on the type of sensor that you employ in this category. They are excellent for identification of the water table, and this may be required in irrigation infrastructure and possible dam locations. This technology is highly recommended when you are setting up irrigation infrastructure. Another and very important use for this technology is they can help determine where the best soil moisture sensor locations are. For example, if you have determined via your EM38 that you have 3 areas of soil moisture across your farm, you would put a different number of sensors in each area, and that would tell you about where to put your irrigation infrastructure and how to determine your scheduling based on that area. For example, a sandy area of your farm, you may have a higher frequency of irrigations compared to another area that may be heavy in clay and can hold water better. There are some disadvantages of using EM38 sensors. They are expensive to run. You need to bring in a consultant typically to obtain these measurements. To determine soil moisture characteristics, you need to do this several times. You need to ensure that the calibrations for the instrumentation is up to date, and most importantly, some technical understanding of the data is required by the farmer in order to use the information correctly. In the next part of this lecture, we're going to look at a suite of sensors. In the plant sensors, we will look at sensing plant water status, sensing plant temperature, and an example of disease monitoring. In the animal sensors, we will look at sensing of livestock. The ability to measure how much water is in a plant or how much water is moving through a plant at any one time is very important if you wish to optimize your water input into your plant system. What I mean by this is if you have some information about how much water is in your plant or your transpiration, that is water movement, you can set ideal irrigation scheduling objectives. The ability to measure plant water status is very important in some plant research, and it is often applied in this context. The ability to measure plant water status either falls into the category of measuring the content of water in the plant or the transpiration or movement of water through the plant. The first one on the list I have included for completeness, which is soil moisture. This is an indirect measurement of plant water status, and we have covered this earlier on in the lecture. Soil moisture can indicate if there is water available to the plant, but it doesn't necessarily tell you if the plant has water. The relationship holds true often. Plant water potential is a measurement that gives you an indication of how much water is available for use in the plant. This is different from total plant water content. Typically, there are two methods of sensing plant water potential, that of a pressure chamber or that of hydraulic conductivity with a commercial product such as a psychrometer. Sap flow is a measurement that indicates the movement of water. Osmotic potential is another measurement that tells you something about the water and the chemical status of the plant. This tends to be used more from a research perspective than a scheduling perspective, and it is tend to used in the context of determining if a plant is in water stress or not. And the last measurement of plant water status is indirect, that of evaporative transpiration. The equipment required for this are weather stations, which we have discussed previously in this lecture, and a suite of algorithms which connect the theory of how much water a plant has used in any one particular area at any one particular time. The pressure bomb is a machine that can measure plant water potential. The plant sensor it is a plant sensor that has been around for some time, and it is used a lot in some industries to assist with the determination of ideal irrigation scheduling objectives, particularly objectives like regulated deficit irrigation. It is used extensively in plant research to determine either plant water status and/or plant water stress. It is what we call a point sensor. That is, it measures one point at one moment in time. It does involve destructive harvest or removal of either the plant or stem. The costs can depend on the unit. The cheaper ones start at about $100 and they go up to thousands. It is important to understand the location of your sensing and the objective of your sensing. The objective will determine your location. You can either sense the stem water potential or the water potential of the leaf. The spatial resolution characteristics of this sensor are dependent on the number of stems and/or the number of leaves that are collected. Often this is limited by transpiration characteristics. What we mean by this is that transpiration tends to readily increase in the early parts of the day. Once you hit about midday, transpiration will stay or remain steady for a while. Depending on how the afternoon is from a climatic perspective, transpiration could continue to rise, could remain steady, or could fall. Therefore, in order to make your results meaningful, you tend to record data across a specific time in the transpiration, i.e. usually around midday when transpiration characteristics are most steady. But again, it does depend on your objective. Plant water potential using a pressure bomb has not been automated to the best of my knowledge, and it requires manual data collection. Therefore, there is a labour component associated with this sensor. Along with the labour component, some technical knowledge is required for both safe operation and correct operation, as well as interpretation of the data. There are certain temporal measurement aspects. If you measure your plants at pre-dawn, before the sun comes up, the water content of the cells is reflected in the measurement. If, however, you measure your plant's water potential during the sunlight hours, you are effectively examining two processes at once: the transpiration characteristics of the plant at this point, as well as the water content of the cells. Please note, you cannot differentiate transpiration and water content of the cells with the pressure bomb measurement during sunlight hours. You just have to accept that it is a combination of both of these measurements. One aspect to consider when operating a pressure chamber is that you understand the operational range required. Different machines have different operational ranges, as different plants have different water potential ranges. For example, vegetables require a low operational range. That's because they have a lot of water and they have a less negative water potential, while eucalypts require a high, up to a minus 100 bar operating range. Most agricultural crops are good up to about 25. From a health and safety perspective, one of the issues with this particular sensor is that it can cause a blunt force trauma or missile. That is because it is under pressure, hence the nickname pressure bomb. If the lid is not correctly attached to the vessel, then under this pressure, as the gas enters the unit, it can fly off and do some considerable damage. Care must be taken to ensure that the lid is correctly placed on before gas or operation is conducted. You also have to consider the leaf and the stem that you wish to analyze. When a leaf is in the sun, it is called a sunlit leaf, and this tends to represent photosynthetic active leaves. A shade leaf, that is one that is not in the sun, tends to represent non-photosynthetic active leaves. Different leaves means different things. The stem is more often used than the leaf because it is a more integrated measurement of the plant water status. The image on the slide is a commercial example of a modern-day pressure chamber. You will see a number of components. Firstly, this equipment has been placed into a case for easily handling and moving around your enterprise. I don't know if you can see it clearly, but there is a metal chamber on the left-hand side towards the back of the case. This is where you put the leaf or the stem. You actually place the leaf and or the stem inside the chamber, and you have the end of the leaf or petiole or the end of the stem sticking out of the chamber. This unit will be attached to some form of gas bottle, not shown in the image. When you are ready to take your measurement, that is, the top of the chamber is correctly assembled, the leaf and or the stem is in the chamber, you open up the gas chamber to allow pressure to be applied inside the chamber. This will then push out the sap. The more pressure required, the more force required to push out the sap, therefore the less water. The dial in the middle towards the back of the sensor is the data collection. It represents bars, and this is shown in minus. There is then a conversion between minus bars to megapascals or kilopascals, depending on what unit you require. Hydraulic conductivity is another way of measuring plant-water relations and can also be used to determine growth potential. A product has been developed by a NASA-funded product. Professor Mike Dixon led a team to develop what we now call the Psychrometer. The operation of the Psychrometer and the principles behind it are quite complex. The sensor is attached to a stem. It actually makes contact with the xylem. The sensor cools a wire junction via a Peltier cooling element. This creates a temperature gradient. what we refer to as the wet bulb depression, can be measured via the psychrometers. A relationship can be correlated between the sample and the dew point measuring junction, and this can give you plant water potential. This work was based on publication in 1984 by Dixon and Shree in a paper called A New Stem Hydrometer Correlated for Temperature Gradients and Calibrated Against the Pressure Bomb. This was published in Plant Cell and the Environment. This sensor tends to be quite expensive. It is called a point sensor. That is, it measures the stem water potential on one stem at one time. This results in obvious poor spatial characteristics. However, this instrument has excellent temporal characteristics, and it has certainly allowed the automation of plant water potential. Before the commercialization of the psychrometer, the measurement of plant water potential was only possible via the pressure bomb, which was manual. This instrumentation requires calibration. One of the disadvantages of this machine is that it requires quite a high level of technical knowledge for installation, operation, and data interpretation. Now we'll move on to Sap Flow. This is based on Granier's thermal dissipation Sap Flow sensors. The components of the Sap Flow system tend to be sensor probes, heat averaging tubes, data cables, power units, data loggers, and external batteries or solar panels. The operation of a Sap Flow is quite complicated. Two probes are inserted in the stem, usually 10 to 15 centimeters apart. The upper probe is heated via a coiled element. The lower probe is not heated and measures the ambient temperature of the stem and its tissues. The temperature difference between the two probes is measured by a T-type thermocouple. The heat dissipation due to the sap movement reduces the temperature difference between the two probes. Therefore, the concept of sap flow is temperature difference is closely related to sap flux density, as described in the two publications by Granier in 1987 and then later by Liu et al. In 2004. The figure on the screen was obtained from the website plantsensors.com and shows the principles behind the sensor, both its components and how it operates. There are many commercial examples of sap flow measurements now available. Sap flow is regarded as a point sensor. That is, it measures the flow of water in the plant at one point. This equipment tends to be on the expensive side. There is a high level of expertise required for installation, calibration, operation, and data interpretation. Certainly, the uptake from a commercial perspective has been limited. That said, it is widely used in research, particularly when evaluating water components and irrigation scheduling components. It has excellent temporal characteristics, but as you can imagine, being a point sensor has poor spatial characteristics. Osmotic potential is a measurement of the potential energy of water per unit volume relative to pure water references. That sounds quite complicated, but from a plant's perspective, it is the water potential or the tendency of water to move in a plant from one area to another due to a number of components such as osmosis, gravity, mechanical pressure, or matrix effects such as the capillary actions in the plant vessels. It tends to be conducted on extracted sap samples or destructively sampled leaf tissues or leaf discs, and currently is not automated. The sensing of osmotic potential currently is a point sensor and can only be conducted by manual operation to the best of my knowledge. It tends to be conducted in research when looking at stress physiology or plant water status research, and particularly used in irrigation scheduling optimization research. It has both poor temporal and spatial characteristics. Evaporative transpiration, or evaporative demand, is a measurement that allows you to calculate the theoretical water use. It does this by understanding how the climate conditions influence a plant's use of water. The climate conditions that are required to be monitored are ambient air temperature, air humidity, wind speed, and total radiation. An algorithm has been developed to determine the relationship of these climatic conditions and how they influence evaporative transpiration and demand. It is worth noting that evaporative transpiration is very dependent upon the boundary layer characteristics. The boundary layer is a physiological aspect of the leaf. It is an area directly underneath the leaf and only composes of about 1 millimeter thick. There are a number of ways that you can measure plant temperature. You can use thermocouples. These have been used in research for many years. Infrared technology can also be used. In recent years, this has come on greatly, as there have been many commercially produced infrared sensors at a price point which is making this technology very usable. Thermistors is another way that plant temperature can be measured, along with optic fibers. Optic fibers tend to be very accurate and measure very small areas, and as a rule of thumb, with the exception of some very intricate research, are not commonly used for this application and will not be discussed here. Thermocouples are a very common type of temperature plant sensing. They are electronic signals sensors that respond to devices in temperature by producing electrical signal. They can be used as a measuring device and/or they can be used as a control device. A thermocouple consists of 2 wires of dissimilar metals or alloys. They are connected to a circuit that contains a voltmeter. The output signal from the voltmeter is usually in volts. A simple conversion can be conducted to change the unit into degrees C, the preferred temperature unit. The image on the screen shows you a thermocouple circuit. You can see the measuring junction point, or where the 2 wires are crossed, a heat source, the voltmeter. Some devices will display the temperature in degree Kelvin. Please note this is different from the preferred unit of degree C. A simple conversion can convert your degree Kelvin to degree C. One important aspect of a thermocouple is that it will measure the temperature change across the whole sensor. Some of your sensor will be in direct contact with your leaf, and this will represent the temperature of the leaf, while part of the sensor will be in contact with the ambient air temperature. Insulation can reduce this error, but it is worth noting. As an actual leaf temperature, the thermocouple can be subject to error due to this important component of the sensor. However, if you are using temperature as a relative sensor, i.e. trying to determine the relative change between one treatment versus another, or one management system versus another, then this is an excellent and cheap sensor. Some of the characteristics of thermocouples worth mentioning. They have excellent precision. They can measure fractions of degrees. They can measure a significant variation or range in temperature. Thermocouple devices can measure down to -200 degrees C and up to 1600 degrees C. The composition or construction of the thermocouple will determine the range. Not all thermocouples can measure across this large range. Thermocouples tend to have a poor spatial resolution, that is, that they only measure a small area of your plant. However, because they are so cheap, you can increase this by taking many measurements. Thermocouples have good temporal resolution. if data collection device is connected to a wireless communication device. Data collection can be manual or automated depending on why you are collecting the data and how much budget you have to collect your data. Infrared sensors are another way for measuring temperature of either a canopy and/or an animal. The measurement infers the temperature from a proportion of the thermal radiation, sometimes called blackbody radiation, that is emitted by the object being measured. There are a number of commercial devices available, and they tend to be referred to as IR cameras. The measurement of IR can be either as a point sensor or as a spatial sensor, depending on how the IR measurement is taken. Temperature measurements range significantly with the device, along with the resolution characteristics. Price ranges tend to reflect both the resolution and the lens characteristics. The output of using IR to measure temperature has led to further applications. Not only can the canopy temperature be measured and conclusions about your management and/or your research resulted from these measurements, but further work to develop what is called a crop water stress index has been conducted. The crop water stress index is a measurement of plant stress, and it is based on the relationship of the canopy temperature compared to that of the ambient temperature. What does the crop water stress index actually tell you? Well, it's quite simple. If the canopy temperature is the same temperature as the ambient, then it may be inferred that there is no transpiration, the process of water movement through the plant. If, however, the canopy temperature is significantly cooler than the ambient, then it may be inferred that there is some kind of cooling mechanism that is occurring. And in plants, this is the process of transpiration or water loss or movement through the leaf. When dealing with crop water stress index, there is expertise required for data interpretation. The image on the slide was collected with some research I was involved in. The images show you the IR data collected across a grapevine or vineyard. The data shows an experiment or the results of an experiment. Ashley Wheaton from the University of Melbourne collected this data by mounting an IR camera onto a balloon and placing the balloon above the canopy. He was then able to take images of the top of the canopy, and this is what you can see on the left-hand side image. You will see that the IR image shows different colours. The colour is related to the temperature. In this key, the lighter the colour, the yellows and oranges, are hotter than the cooler colours of purples and blues. The temperature canopy ranges from the cool 28.5 degrees C up to the hot 33.7 degrees C. The air temperature on the day of collection was 30 degrees C. The experimental setup was put together by Unumber Wines in collaboration with CSIRO and SARDI. On the right-hand side, you will see another version of some mounted IR sensors. These continuously measure the top of the canopy. This was one way we were looking at trying to automate the collection of IR temperature to calculate crop water stress index. We were then hoping to use this as both indications of plant stress and as an irrigation strategy. The crop water stress index has been shown at the proof of concept basis. That is, it can theoretically be used as an irrigation scheduling tool. When you calculate crop water stress index, it is a ratio, and the ratio sits somewhere between 0 and 1. The lower the ratio, or the more towards 0, the more stressed the plant is. It is what we call a block or spatial sensor. And it has another advantage, that it is a direct measurement of plant stress. I must emphasise though, what you have seen here today is a product of research, and there are many steps to commercialisation. These include the automation of the infrared canopy measurement itself, and the wet and dry references which are required in order to calculate the crop water stress index. Thermistors are another type of sensor that can be used to measure the temperature of a leaf. The measurement, put in simple terms, is based on the resistant changes. It is where thermally sensitive semiconductors whose resistance will vary with temperature. Once you understand the relationship between the resistance and the temperature, you can then put together a simple calibration curve which will enable you to determine the temperature from the resistant change. Thermistors tend to be made from metal oxide semiconductor materials, which is encapsulated in a glass or an epoxy bead. Thermistors are used as point sensors. They are very cheap, the thermistor itself. You can easily get a good thermistor for 40 cents, say. You need to collect them to some kind of data logger, and you need a data communication protocol or requirement in order to collect them in a farming situation. This measurement has the advantage of being automated with excellent temporal resolution. It is a system that suffers from poor spatial resolution. When you consider the area of measurement, there is only a small area of measurement. They have similar issues to that of thermocouples in that they measure the sensor point of contact and the leaf, and there are some areas of non-contact which results in an ambient measurement. Therefore, an insulation component to the thermistor is often wise in order to get accurate data. They tend to be used in research settings rather than from a commercial framework. This is not because of their cost or the data interpretation, but rather due to the fact that they only measure a small area of the leaf temperature. Another type of plant sensing is that of sensing for disease or disease prevalence. There are several examples of disease prevalence monitoring on the market. The only one I will discuss here is the leaf wetness sensor. Decon, which is supplied by ICT in Australia, is a commercial example of a leaf wetness sensor. It simply measures the surface wetness. The surface wetness is measured by a dielectric constraint of the sensor on the upper leaf surface. This can then be correlated to disease susceptibility. For example, you need damp, warm days for downy mildew. So many days in a row of certain climatic conditions significantly increase the chances of the disease outbreak. The following is an image of the leaf wetness sensor. This is a point sensor. It has good temporal resolution but poor spatial resolution. There is an argument in this application that you do not actually need a large spatial resolution. Now we're going to touch on animal sensing systems. I'm going to start with an overview of livestock monitoring and sensing. The underlying purpose of these sensings is to increase productivity and/or economic return. The mechanism by which the sensing can increase productivity is through improved efficiencies, such as disease reduction by early disease detection and therefore more effective treatment. Other components of measurement include things like carbon emissions or methane emissions, and monitoring of all farm inputs. One example of a livestock monitoring system is that of a live fence mechanism. This enables containment. Soil moisture for pasture growth is used as a monitoring device to increase the efficiency of the food production. The better pasture growth, the better the milk quality and quantity that the cows can produce. Cow movement is sometimes wanted to be investigated. This enables not only productivity outputs to be speculated, but also you can monitor health aspects of the herd. There has been some research on individual animal sensors. These are often coupled with RFID tags. These sensors can detect things like animal behavior, the temperature of the cow, which can indicate a number of components both in milk production and health. Most of these systems are connected by some kind of data communication, and often in a dairy type environment this needs to be wireless in the form of radio sensors. They are usually what we refer to as static systems. That means the sensor does not move. Of course, when an individual animal is being sensed, this sensor will be moving all the time, and this is more of a dynamic system. The attached sensor on the image is one such example of a cattle sensor. You will see on the top of the sensor there is a solar powered unit. This is how power is supplied to the unit. There is a radar which enables the information to be communicated. This device will enable the cow's movements to be sensed along with its temperature. When you look at the role of agricultural research and sensing, you will find that sensors play an important part. CSIRO has set up a project to monitor animal behavior with the potential for improving livestock management tools. The technology allows scientists to monitor livestock remotely, their social interactions and spread of the disease and calf development. This technology may be very useful in tackling such issues as animal welfare. Another very important sensing system is used by the National Livestock Identification System. This is Radio Frequency Identification, or RFID for short. RFID is a wireless non-contact use of a radio frequency electromagnetic fields to transfer data. It enables the automatic transfer of data. This data will identify and track tags attached to the objects, i.e. it can identify individual livestock and track their movements. Tags can be powered or they may not be powered. They all have data storage capacities. The following video, you can see the link on Moodle, tells you about a commercially available RFID temperature sensor. This is described as a tiny passive RFID temperature sensor that also enables automatic daily temperature recording of the animal, as well as the identification aspects that are required for livestock monitoring. Please pause the lecture here and watch the following video. You can insert notes from the video here. The following abstract is from the paper entitled Emergent Sensing of Complex Environments by Mobile Animal Groups by Andrew Baddeley et al. It is an article which talks about the capacity to exhibit collective intelligence in a herd. The sensing technology really enables the understanding of this collective intelligence. In this paper you will see the methodologies and how the sensing plays a role in this kind of research and its outcomes. Individual animals were monitored, where their speed in response to a local, their scales and measurements of light and social interaction with others was recorded. This was shown to be an appropriate and cost-effective for a robotic agents and measurement of as a good sensor for measuring animal, livestock, social interactions. I'd like you to pause the video here and watch the following YouTube video. This is entitled Scottish Cattle UHF RFID Demo. It is a video that shows you a demonstration of what is referred to as the passport for cattle. It is an electronic recording device. It identifies each individual cattle and a suite of information pertinent to that cattle's production. Now I'm going to present a case study developed in horticulture. This is based on work that myself and other colleagues at the University of Melbourne conducted as part of a Science and Technology Innovation funded grant. The objective of this research was to increase irrigation productivity from improved quality, value of horticulture and viticultural produce in the application of real-time automated irrigation. In this case study, we selected Pink Lady apples and looked at their commercial value of produce. A comparison of standard manual irrigation practices was conducted and compared to a real-time closed-loop automated irrigation. What we mean by real-time closed-loop automated irrigation is that the data was collected in real time, that there was a loop of information, that is, history informed the data. And the automated component is that irrigation solenoids were turned on and off based on the algorithms that was obtained from the data collected and the levels that we developed. The figure on the slide demonstrates the success of real-time closed-loop automated irrigation practice that we were able to conduct and perfect. We have soil moisture at 40 centimetres, which was recorded. The thin black line shows what the recordings of the soil moisture was throughout periods of the growing season. The black line at the top demonstrates the maximum soil moisture, and the black line at the bottom demonstrates the minimal set soil moisture. We wrote algorithms and developed calibrations that were specifically set up for our crop. The red line indicates the automated irrigation events. This is when the actuator, which was a solenoid, was turned on and off based on the soil moisture percent. The soil moisture solenoid was turned on when the soil moisture reached 37, allowed to irrigate for a period which changed in time depending on the conditions, and where it was switched off at 41%. In apple crops, the number or the potential of apple load is set by the number of flowers attained at any one year. These experiments were conducted after flowering, as it was deemed critical to keep the potential apple number during this experiment. The standard manual industry irrigation practice was compared against the real-time automated irrigation. Apples are sold according to classes. Lower classes receive smaller amounts of money. Our industry standard produced a lot of low class, i.e. 2 cents an apple classes. An observation we noted with our real-time automated irrigation was that our apples increased in size. As this was an important component of the class, the number of apples in our class increased. Thus, we were able to increase the value of the crop. The exact value of the crop was calculated. We were able to improve our economic water use efficiency from $2,671 per megalitre on the manual or traditional irrigation to $4,625, which was the real-time automated irrigation. This represented a 73% increase in gross returns. You will note that this resulted in a larger volume of water being delivered on the automated versus the manual, with only a small percentage increase in total yield. However, this small increase allowed more apples to go into a higher class, and therefore we got a better return. We were able to establish in this experiment a 74% increase in economic water use efficiency for this year. It should be noted, on commencement of this experiment, we determined relationships between plant water status and soil moisture on this site, and therefore we were able to set very accurate maximum and minimum soil moisture depletion levels. These findings demonstrate the potential of automating irrigation systems based on collected data. The second case study I'm going to present today enables a comparison between soil moisture depletion and evaporative demand sensing. These experiments were conducted at the University of Melbourne by Cooley et al. During the period of season 2010. A number of strategies were identified. Time, date, which is based on pre-programmed history. Soil moisture depletion. Some comments to make about these treatments. The spatial variability of soil moisture is something that needs to be considered. This is overcome in evaporative transpiration, which is based on climate. Crop water stress index is a plant-based strategy, and as economically you're trying to understand and irrigate the crop so that it performs at its best, it can be perhaps concluded that a plant-based sensor is the way forward. As a sideline, this technology can also be used in such industries like dairy. They typically irrigate their paddocks via flood irrigation. Water will be ordered, it will pass through a channel, a gate will then open, and the water will cross the paddock. Real-time monitoring can be used to trigger the gate opening and closing to optimize your irrigation. The table on the slide was produced by DASA in 2010 and gives an overview for this technology in dairy. Despite the rigor and time that was spent by the scientists in placing probes and choosing good locations based on an understanding of such parameters of soil salinity, soil pH and soil density, we still got a 6.3% variation. This variation was calculated from analysing the total variation from all of our probes. It only takes into account the 25th percentile from the mean. Therefore, it is a very conservative estimation of the variation. A larger variation can be found in commercial systems. This variation represented a difference from irrigation from 5.2 to 5.9 megalitres per hectare, depending on which probe you selected. This equated to a gross value range that varied from 62,000 to 71,000 cost. These costs were based at pack-out and did not include production costs. Returning to the case study, soil moisture sensing and evaporative demand sensing were conducted at this commercial orchard and vineyard that's demonstrated on the slide. The blue boxes represent irrigation areas. The red dots on the slide represent the location of soil moisture probes. These were placed on certain parts of the block and were based on information obtained from EM38 and from experimental requirements. The green probes are probe locations that have been used in this orchard and vineyard for many years. Some facts worth noting about soil moisture measurement. In this example, the orchard vineyard area summed 25.05 hectares. The commercial soil moisture monitoring area was about 0.02%. The experimental soil moisture monitoring area, which comprised of many soil moistures, only totaled 0.25% of the area. Evaporative demand was based on a weather station located in the centre of the farm. Evaporative transpiration represents 100% of the area, because in this microclimate it is fair to assume that the evaporative transpiration demand does not vary over the site. Different crops require different soil moisture depletion categories. For example, apples operate best if they don't experience water stress, while periods of growth that grapevines go through produce a better composition of their berries if they do receive a deficit irrigation. So we address the question, could deficit irrigations be applied using this technology? The answer is yes. When a 90% soil moisture depletion was applied to a Shiraz crop and compared to a full moisture depletion, we saw that the number of irrigation events increased, the volume per irrigation decreased compared to the full moisture irrigation. The soil moisture depletion was compared to the transpirational demand. This was an irrigation scheduling procedure that we based on the concepts of ET, or evaporative transpiration, where evaporative transpiration is the loss of water from a vegetative surface through the combined process of soil evaporation and plant transpiration. As part of this treatment, we assembled a weather station to FAO 56 standards, which measured the climatic conditions of ambient air temperature, air humidity, wind speed, and intercepted light. The season we conducted these experiments, there was a large amount of rainfall and precipitation, so we were only able to conduct them during drying periods. We did, however, during these dry periods, demonstrate that there were differences between irrigation automated by evaporative transpiration and irrigation delivered by soil moisture depletion. The figure on the slide demonstrates these differences. Soil moisture depletion is recorded and is shown by different colours of lines going across the figure. At the base of both of these graphs are both red and blue columns. The red columns represent rainfall, while the blue columns represent irrigation applied. The soil moisture depletion had less irrigation events, 2 in the period illustrated, but they were a greater volume than the evaporative transpiration, where 3 irrigation events of a smaller amount of water was delivered. Irrigation was triggered on an 8 mm accumulation. Due to the season that we conducted these experiments, we weren't able to demonstrate yield or quality parameter increases in this technology. But we do believe in the periods that we were able to deliver the irrigation strategy that it does show the potential for differences in both yield and quality as the number, the frequency and the amount of irrigation events vary. That brings us to the end of this case study. The following is a table that I'd like you to study. This demonstrates a number of measurements, the description of that measurement, and gives some details about its sensing, whether it's a spatial or temporal sensor, whether it can be automated, and if the data can be gathered in real time, and some additional information. Please study this for the assessment next week. The following 2 slides list some considerations that you should think about if you would wish to put a sensing system on your agricultural enterprise. The first thing to think about is, why are you sensing? What is your objectives? Is it for compliance and standard platforms? If so, this will direct many aspects of the sensing system. Or are you sensing to improve efficiencies in your enterprise? Does this mean that your sensor will measure the improved efficiencies directly or indirectly? These are important pieces of information to describe and understand. The next question you should ask is your sensor fit for purpose? This can mean many things. One of the most important things to establish is it reliable in the farm environment? We call this robust. Many of the early sensors were not robust. Many of the newer commercially available sensors are robust. That is, that they will work efficiently over time in that kind of environment. You need to consider the climate and any physical characteristics of the farm environment when you're considering how robust your sensing equipment may be. Does your sensing equipment collect data at the frequency which is fit for its purpose? What I mean here is, are you collecting the data at the right frequency in order to determine your efficiency or your standard protocol? Does it collect the data once a day and you need to find it out more times than that? That sort of question. Usually it's the other way around. Usually you have more temporal data in automated sensing systems, and this can cause data handling issues. So understanding exactly what you wish to measure is quite important. And does your sensor adequately represent an area or a variation in your enterprise? This would be your spatial characteristics. Have you got enough of this particular sensor in place? If you haven't, this could completely skew your results, and therefore you may not achieve the efficiencies that you're after. Or worse than that, you may not be compliant for the standard that you are trying to achieve. Does the data you collect from your sensor reflect your purpose? This might be a strange question to ask, but it really is one to consider. I'll give you an example. If you're after how much water is used in a plant, a commercial enterprise may suggest the ultimate of this is soil moisture monitoring. Now, in some situations, the indirect measurement of soil moisture monitoring is adequate and in fact very useful. But there are certain situations where this is not fit for purpose. Therefore, understanding how the sensor works and its underlying assumptions are very important. And finally, before you commit to any sensing system, an understanding of the economics involved is essential. With most sensing systems, there is usually a large outlay in the system itself. This will be the cost of the individual sensors, some form of communication device or devices, and infrastructure to enable both the operation of your sensor and its communication. Does any part of your sensor involve manual labour? It is often not so essential to consider the setting up of the sensing system, but rather routine collection of data. And will your sensing system actually increase production or productivity or efficiency? This can be a very hard thing to determine in some measurements. So that brings us to the end of Lecture 12, Part 2. So in summary, you will have been exposed to some examples of climatic, environmental, soil, plant and livestock sensors. Each of these categories you should be able to give an example of the systems, their associated advantages and disadvantages, the function of the sensing, why are you sensing, the temporal and spatial characteristics of the sensor and the sensor system. That brings us to the end of this lecture.